Okay, so let's start from where we stopped. So here we have plus, minus, plus. Right, so our answer here is 4 into 9 minus 12 minus 8 into 7 times 9 is 63. That's 63 minus 8 plus 13 13 into 21 minus 3. So this is 4 times minus 3 is minus 12. So this is minus 12. Minus 63 times 8 minus 8 is 55. 55 times 8 is 440. So minus times, okay, that's minus 440 plus 13 times 18. That's 2, 3, 4, Nigeria. Right. So 2, 3, 4 minus 12 minus 440. So answer is equals to minus 128. So that's the answer for the determinant of this. So we move into today's topic, which is linear algebra. Linear regression. There you need to save. So let's move into linear regression with a single variable now. Right. On Wednesday, we'll do linear regression with double variable. Then on Friday, we'll go into logistic regression. In the previous class, I made an explanation that I'm going to go over again, just for emphasis sake, right? I said machine learning, ML, is divided into two. The first one is supervised learning. And the second one is unsupervised learning. Supervised learning is divided into two once again. This is divided into regression. We have regression problems in supervised learning, and we also have classification problems. And then unsupervised learning is divided majorly into one. That's a clustering problem. So we have clustering. So like I've explained, in regression problems, regression problems help us to solve problems where we have a continuous variable. So for example, we are trying to predict the price of the house. Let's say the price of the house is $50. right? And the price of the next house is $70 or 70.5, right? So this is a continuous variable, right? This is what we use regression problems to solve. We use classification problems to solve problems of yes and no. Is the tumor cancerous, right, or malignant? Oh, sorry, is it malignant or non-malignant or non-malignant? Is the email a spam email or not a spam email? Is the transaction a fraudulent transaction or not a fraudulent transaction? So it's either 0 or 1, right? So we use classification algorithms to solve classification problems. Now, the difference between supervised learning and non-supervised learning or non-supervised learning is that in supervised learning, the output is given, right? So you use the output to train your model. And I remember that I showed you examples of that in the last class. I don't know if I still have. Okay, I've closed my Kaggle now, but I remember I showed you examples of that, and I still would probably show you examples of that. But in supervised learning, for example, let's say you have customer data, right? We want to group our customers. We don't have any target variable, but we just have customer data. We want to group our customers under different classes, right? So we use clustering algorithms to solve problems where we don't have a target variable. But supervised learning, so in supervised learning, there's a target variable. Right, just remember that. Or there's an output, which is usually Y. But in unsupervised learning, there's usually no outputs. So it's just full of features, right? So in this course, I attempt to explain the simplest regression algorithm, explain the simplest classification algorithm, and also explain the simplest clustering algorithm from the mindset of a mathematician. So I'll show you the mathematical intuition of all these three algorithms, then we'll go into Python next month, right? So let's go into proper linear regression. Okay, I remember I think I still have the data. So for example, here is um, a train set for, what do you call it now? The Titanic data sets. So you can see on Titanic data sets, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 input variables, and then we have one target variable, which is our output variable, which is 0 and 1. So 0 means the person did not survive. 1 means the person survived. So we are supposed to use this data set to build a model that can predict if an hypothetical traveler that goes on this Titanic ship is going to survive or not. We are looking at factors of, so we are supposed to bring out factors of survival inside this data set and predict if newer customers or newer travelers are going to survive or not. So this is an example of a classification algorithm or a classification problem, right? So let's go into linear regression with one variable. Let me see how this would be. All right. So this is the central dogma of machine learning or data science. All right. This is the central dogma. I'll need to put this down. So for example, I want to have this. So yeah, we want to estimate the price of a house based on the size of the house. So this is the y-axis, this is the x-axis. Again, this is the output variable, this is the input variable. This is the size of the house, and this is the price of the house. Right. So in a linear regression model, we'll have something like this. So this is our model that fits our data. So the size of the house here corresponds to a particular price. So the size of this size corresponds to a particular price. So you can predict that if the house has this size, then this is supposed to be the corresponding price. If the house has this particular size, then this is supposed to be the corresponding prediction for price, right? So we have training sets. This is our training set. I just showed you an example of a training set. So this is our training set. I need to write this down and look at it very closely. This is our learning algorithm, which is linear regression, right? This is our learning algorithm, which is linear regression for now. This is the size of the house. Size of the house. This is the size of the house. Here we have H, right? Which is the hypothesis. And here is the estimated price. Estimated. This is the estimated price. So we draw this like this, right? This is just basically what we do in machine learning and data science, right? And we draw this like this. And we draw this like this. And then we draw this like this. So this has this arrow. This has this arrow. Obviously, that's the arrow. And this is that has the arrow. So you take your training set, right? You put it on the learning algorithm, which is linear regression in this set. Then you use the size of the house, which is what we are using to predict, which is our input variable, right? We put it through this hypothesis, right? The hypothesis that y equals to mx plus c, which is the hypothesis for linear regression, and then we use it to estimate the price of the house. So basically, I'm just saying that h is a function that maps y, that maps x. So this is x. And this is y, obviously, right? And this is h. So we are basically saying that h is a function that maps x to y, right? Remember, this is linear regression with one variable. So the variable we are using is the size of the house. So the hypothesis h, right, is the function, right? The function, right? That a function that maps x to y, right? I mean, that's obvious. But you know, in secondary school, we used to have y equals to mx plus c, where y is what we have here, right? Obviously, x is what we have here, our input variable. M and c are constants. And in machine learning, we use theta to represent our constants. So we'll be doing, instead of this, we'll be doing h of x, which is our hypothesis, equals to theta 0 plus theta 1x. So we'll use theta 0 to represent c, right, and theta 1 to represent m, right? So this will be our, there will be theta somewhere here. So this will be our transformed hypothesis for machine learning, for linear regression. So let's see, let's plot the graph once again, right? So let's plot the graph once again, just for emphasis sake. So this is how our linear regression model looks like. So this is my y-axis once again. Forgive my writing, please. This is my y-axis, and this is my x-axis. So we can have a line like this. So let's say we have this is our data point. All right, let's say this is our data point. We can fit, you know, we can fit a line through our data point like this, right? And this line is going to be what we tie to h of x. Of it, theta somewhere equals to theta 0 plus theta 1 x. Does this make sense? All right. So this is just basically a simple intuition of linear regression and how it works in machine learning. The next thing we'll be treating is cost function. We'll be treating something called cost function. After cost function, we'll be treating something called gradient descent. And if you've gone through the machine learning crash course, sorry for my Ijebu accent. If you've gone through the machine learning crash course, you would have come across something called cost function and gradient descent. But I'll just give you an intuition. Note that you don't need to actually go deep into the math. All you just need is an intuition into what is happening when you write code, right? Right. So let's say we have a training set. Okay. So let's say we have a training set now. I hope I have time. Here we have size and width, which is x. And here we have price. One, yeah, which is y. So we have 2104. Then we have 1416. Then we have 1534. And we have 852. We have 852. On the price angle, we have the corresponding price as 460. 232, 315, and 178. Right, so let me just, so for this particular house, the price is $460,000. For this particular house, the price is this. Right, of course, you understand that. What we do in machine learning is that we solve, the computer tries to solve for this theta or for this constant. And if you go back to the class where I taught you on linear dependence and linear independence, you see that I mentioned something like that. In machine learning, what the computer tries to learn is theta, which is our constant, right? So I'll give you an example of that. If we have this, right? We have this. I'm just trying to show you how different values of theta gives us different characteristic or different behaviors on the straight line graph. So if theta 1, for example, let me label this as 1, 2, 3. Then 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1. 3. For example, if our theta 1 is what is call me back, Abel. Call me back. Call me back. If our theta 1, theta 0 is 0.5. And then our theta 1 is equals to 0. Then we'll have a graph like this. Right? 1.5 in the middle here. So we'll have a graph like this. Right? If our theta 0 is 0, so we start from the origin. If our theta 0 is equals to 0, and then our theta 1 is what? 0.5. Well, we are going to have a graph that looks like this.
Here are some results from a search.
Not necessarily accurate, right? But we're going to have a graph that looks like this. And on the other hand, if our theta 0 is equals to 1, and our theta 1 is equals to 1.5, we're going to have a graph that looks like this. So our theta 1 starts from 1. Theta 0 starts from 1 here. Theta 0 starts from 0 here. So theta 0 starts from 1 here. We're going to have something steeper than this. Since this was 0.5, it should be steeper than this. And so we're going to have a graph that looks like this. Right. So this is to show you how different values of theta gives your data different attributes in 2D. I can't go 3D now because it will be very hard to draw, but this is how it looks like in 2D. Right. So the basic idea, all right, I need you to write this down. The basic idea is to choose theta 0 and theta 1. How do I represent theta on the keyboard now? Theta 0. How do I represent theta now? Okay, let me use Q. Theta 0 and theta 1. So that h of x, which is our hypothesis. Remember h of x, right? So that our hypothesis is close to y for our training examples. So write this down and I'm going to explain. So here's what happens. This is y. Here's what happens. So this is our training sets, right? This is our training set. This data is real life data. But let's say we run this algorithm, like we run this data through a model, and then we use that same model to give an hypothetical output P, right? And then now the size of a house, of this same house, now gives me let's say 470. the size of this one, this size returns a price, let's say 1,500. For example, what are we going to say? We're going to say our model is very inaccurate, right? Right. So we're saying that the idea of the mathematical idea in machine learning is that we want to choose our theta 0 and theta 1 such that our model is going to be able to predict this same exact prices. Of course, you know that in production, you will never be able to get the same exact prices, but you want to be able to get 459 here. You want to be able to get 231 here. You want to be able to get 316, for example, here, even if you cannot get 315, and you want to be able to get at least 176 here, right? So you want to choose theta 0 and theta 1 such that your h of x is close to y, right? So this is our h of x, which is our predicted value, and this is our y, which is the value that we add in our data, right? We want to be able to choose theta 0 and theta 1 such that h of x is very close to the actual value, right? Which is basically the idea of machine learning. And to do that, we use something called cost function, right? Let me write this down for emphasis sake as well. Let me write this down for emphasis sake. We measure the accuracy of our hypothesis by using the cost function. So I'm basically saying that we measure how close our predicted variable is to our actual variable by using cost function, right? We measure how close these two. We measure how close these two are to each other by using an algorithm called cost function, right? But what is cost function itself? Cost function is a minimization problem, right? I'm supposed to write that down again so that you don't forget. And please make sure you are writing down. Cost function itself is a minimization problem, and this is the formula for cost function. Um, right. So this is formula for cost function, right? We have a summation. This is summation of h of x, right? This x is in a bracket. Right? H of x is our predicted variable, don't forget, minus our actual variable. So we are trying to say this minus this, right? All squared, right? On top of this summation is an m, where m is equals to number of training examples. So for example, in this data, we have 4 training examples, right? So M here is going to be equal to 4. So let me write down just in front of this, let me write down minimize, right? Then under it, I'm going to write down theta 0, comma, theta 1. So we're trying to minimize theta 1 for theta 0 and theta 1 for this entire problem, right? That's just basically cost function. Of course, this is the actual price. This is the actual price. This is the predicted price. And yes, this is the sum of training examples, right? All we are doing, of course, like I've explained, all we are doing here is to minimize the error between the predicted price or the predicted output and the actual output, right? So here is what our final formula would look like. So we're going to have a summation. We're going to have a summation into these big brackets. Then we have small brackets here. H of x h of x minus y, all right? Then all squared. On top of this, instead of having an m, I'm going to have a 1 minus 2, 1 over 2m. This is the regularization property, but there's no need to go into why we did 1 minus 2m now. Then let me have a minimize, right? Minimize theta 0. Then comma theta 1. So this is the final formula. So what this means is that we want to find the smallest value of theta 0 and theta 1 and theta 1 that makes the predicted variable very close to the actual variable. We want to find the smallest value of theta 0 and theta 1 that gives us the most accurate model. That's just basically what cost function allows us to do. Remember, we say that we measure the accuracy of our hypothesis by using a cost function. And we also said that I wrote something else, I find it. So we are choosing theta 0 and theta 1 such that h of x, which is our predicted variable, is very close to y for our training examples. I want to believe that that is done. So this would equals to j in brackets theta 0 comma theta 1. So this is our cost function. So please note down your questions. I'll be taking your questions in the next class, right after this entire thing. So this is our cost. the cost function. If you take and of course here this is called mean or squared error cost function. So it's not like this is the only type of cost function we have. There are other types of cost function, but we use this one to explain machine learning to beginners, and this is what I linked with anyways. This is called squared error cost function, or sometimes you can see it as squared error function. It's called cost function. In some other courses, you can see it as squared error function. Just remember that it's all the same, one and the same. Cost function is cost function, right? In the machine learning crash course that I sent to the group, you will see something called loss function, right? Loss function is the same thing as cost function, but this is used to refer to the error for a single training example. So if we find value of θ0 and θ1 for just this training example, right? For just this training example, then we found our loss function. But if we find the error for all the training examples, then we found our cost function. It's used to, I need to write this down as well, used to refer, because you would, for the rest of your life as a machine learning engineer or as a data scientist, you keep hearing cost function and loss function. So it's just good that you understand what it means now. Used to refer to an average of the loss function over the entire training set. Right, so once you find the loss function for the entire data set, then you call that cost function. Don't forget, we use cost function to find the constant θ0 and θ1 that makes our hypothetical, or that makes our predicted variable the closest, or if possible, the same thing as our actual variable, right? So let's go into some further intuition. Let me see if I still have some time, or I just pause this recording right now. We'll go into some more cost function intuition in the next video. Thank you.